Problem 4. An internet service provider uses 50 modems to serve the needs of 1,000 customers. It is estimated that at a given time, each customer will need a connection with probability 0.01, independent of the other customers. A. What is the PMF of the number of modems in use at the given time? B. Repeat part A by approximating the PMF of the number of customers that need a connection with a Poisson PMF. C. What is the probability that there are more customers needing a connection than there are modems? Provide an exact as well as an approximate formula based on the Poisson approximation of part B. Well, for this question, we need to remember what a PMF is, which can be here, and we also need to come up with a way to solve the problem. As it's asking for how many number of modems will be in use at a given time, I am already thinking about using a binomial PMF. A binomial PMF, if you remember, describes the number of successes in n-independent Bernoulli trials. We want to find the PMF of the number of modems in use at a given time. Well, what is the number of modems in use, let's say for 3, right? Let's say we want to find out the probability that 3 modems are at use at any given time. So that means out of 1,000 customers, right, 3 of them need to be using a modem, right? Now this could be, now let's say here we have customer 1, here we have customer 2, here we have customer 3, customer 4, customer 5, customer 6, all the way to customer 1,000, right? Well, customer 1, customer 2, and customer 3 could need. Customer 2, customer 4, customer 5 could be using the modem. Customer 6, customer 1,000, customer 2nd could be using the modem, right? And so on and so forth. And we need to find the number of different ways that these 3 customers could be chosen, which is what this part of the formula does, the n choose k. Let's say we have 1,000 customers, right? And we choose 3 of them. And we multiply this by the probability of success. And here we will be modeling success as the probability of them needing a connection to the power of k, which will be 3, times the probability of them not needing a modem with 1,000 minus 3, which becomes 997. So this is the probability, right, that 3 customers need a modem. Now, we can rewrite this as 1,000 choose k, 0.01 to the power of k, times 0.99 to the power of n minus k. Now, this gives you the probability, right, that they will need 3 modems, 4 modems, 5 modems. However, we're being asked for the PMF of the number of modems in use at any given time, right? The number of modems in use. Now, why does this matter? Well, what's the probability that 1 modem will be in use? Well, that's the same probability of the customers needing 1 modem, right? But after the 50th modem, right, if the customers need 53 modems, right, still only 50 modems will be in use at any given time. Now, to make this more simpler for you guys to understand, we can write the PMF of, let's say, x, and let's say x is the number of modems in use at any given time. Right? We will write it like this, is equal to this formula that we came up with. Right? However, this only holds for k is equal to 0, 1, 2, etc., etc., up to 49. Now, why up to 49? Well, let's think about it this way. The probability of 50 modems being in use at a time, right, is the probability that the customer needs 50 modems, or the customer needs 51 modems, or there are 52 customers who need modems, or there are 53 customers who need modems, all the way up to all 1,000 customers needing modems at the same time, because there's a total of 50 available. So if 1,000 customers need modems, only 50 of them will be in use. So all of these probabilities get summed up into the probability of 50 modems being in use. So how can we write this? So actually, we can write this pretty simply. We can actually write and get this formula pretty easily. We just take the formula that we got above, right? And we just sum it up. We sum it up from k is equal to 50, k being the amount of customers that need a modem, all the way up to 1000. So we're adding up all the probabilities after and including 50, right? The probability that 50 customers need a modem, the probability that 51 customers need a modem, all of them into this right here, the probability of 50 modems being in use. Now, don't get confused. Here, this is the probability, right, of how many customers need a modem. But this whole thing together is the probability of 50, all of the modems being in use, right? These are two different probabilities and two different meanings. So we get our answer as here. This is our probability. Now it only goes up from 1 to 50. So this is true for k is equal to 0 to k is equal to 49, and here is equal to k is equal to 50. If 51 is inputted here, which would be the probability of 51 modems being in use, what is that? Well, it's 0 because we only have 50 modems. So there's no possible chance of 51 modems being in use. It's like saying what's the probability of flipping a coin and getting 6, right? It's not a dice, it's a coin. You can't. The probability is 0. Even though you can input it into the function, it has no way of happening. Now for part B, we need to repeat part A by approximating the PMF using a Poisson PMF. Now let's remember, what is a Poisson PMF? Well, a Poisson parameter approximates the binary PMF when n is large and p is small. And as we can see here, actually our n is very large, it's 1000, and our p is indeed small, it's only 0.01. Lambda is equal to n times p. And here we have n is equal to 1000 and p, which is the probability of success, which is 0.01, which means our lambda is actually equals to 10. Now plugging 10 into this formula here, we get px of k is equal to e minus 10 to the power of k divided by k factorial. Once again, this is only true for k is equal to 0 up to 49. For k is equal to 50, we use the same logic we used in the previous section, which is we sum up our following formula from all k's equals to 50 up to 1000. Okay, easy peasy. We basically do the same thing as the last section. Well, for part C, what is the probability that there are more customers needing a connection than there are modems? Provide an exact as well as an approximate formula based on the Poisson approximation of part B. Now let's think about what this is actually saying. What it's saying is, what's the probability, right, of 51 customers or more needing a connection, right? Because it's asking, what is the probability that there are more customers needing a connection than there are modems, right? So we start at 51. That's the point where we all have extra customers needing modems, right? A customer can't find a modem. Well, this is actually pretty simple. We just use the formula we found in the part A, which was this, if you remember. However, this time we just take it from 51 up to 1000, right? So this is the event, right, where 51 or more customers need a modem, right? So if you remember, in part A, we started from 50. This was the probability that 50 modems are in use, but now we're finding the probability of more than 50 people needing a modem, which is 51. We have to start from 51. Again, for doing this for Poisson, we just do the same thing. We take the value that we found, and instead of summing it from 50, we start the summation from 1,000, easy peasy.